Okay, so on this picture, if it comes out of your hand at 30 meters per second and it goes away from the Earth, what's going to happen to its speed during that next second? What's the Earth's gravity going to do to the speed of that object if it goes away from the Earth? Well, it's called Earth's gravitational constant because it's constant. What's constant? Your speed will change by 10 meters per second every second. If you come toward the Earth, I'll increase your speed by 10 meters per second every second. What if you go away from the Earth? Is everybody with me? What if you go away from the Earth? I was going 30. A second later, I'm only going 20. Huh. And then how much? Then I'm going 10. Huh. And then I'm going what? Huh. Look at this. Think about this. Not counting air resistance. Ready? I'm in the air 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, 6 seconds. If you throw, and not counting air resistance, if you throw a ball in the air for 6 seconds, it's in the air for 6 seconds, half that time it went up and half it went down, isn't it? So how much? How would you plug that into an equation? Like if I started right here and I say, how fast are you going to be going at the end of 3 seconds? What equation would you use? How fast is this ball going to be going if you let it fall for 3 seconds? What is it?
Delta something over delta speed over delta acceleration.
No,
Difference in acceleration or the difference.
It's actually a little easier than that. The free fall equation for how fast is what? What's the free fall equation for how fast?
I think big behind.
V equals GT, isn't that right?
Yeah.
Okay, so if I let it fall for 3 seconds, yeah, it was in the air for 6 seconds, right? But only 3 seconds was it falling. So put that in there, and what's 3 times little g? 30 meters per second. So it would be going 30 meters per second, wouldn't it? What if I let it start at 30 meters per second? How fast will it be going 3 seconds later? So 30, 20, 10, 0, wouldn't it? Isn't that right? Okay. So here's the tricky part. Okay, I'll tell you, it's on the test. Here's a test question. What is the velocity of this ball at the top of the arc? This is not the tricky question. That's 0. What is the acceleration of the ball at the top?
0. No, wait. It's 10 meters per second, or per second squared.
You're right. It's always that. Always. Now, you don't like that because you know at some time at the top the ball's sitting still. But the definition of acceleration says you've got to give me 2 velocities. You either got to get me the one at the top that was right before it stopped and the one when it stopped, or when it stopped. You got to give me 2 velocities. You got to. And you pick any 2 times on that trip and figure out the acceleration, you'll get 10 meters per second squared. So the acceleration at the top, you can't give the acceleration of a point. You get it? I can give you the instantaneous speed. I can't tell you acceleration of 1 point. But you give me this point and the point right before you got there, it's going to be 10 meters per second squared. All right. Well, I want to show you, I think I have it. Forgot to check before I got, and if anybody, I might need to trade $1 with somebody. Let's see. Yeah, mine's not too bad. Mine's pretty good. Mine's pretty good. It's got a little folder. So what I'm going to do, okay, that's pretty good. That's pretty good. So what I do is, if you'll go to page 55, I'll show you a little trick, and let's show you the physics of it, okay? So here we go. Now, you know, whenever you do a trick with somebody, you have to make sure you really know the ins and outs of the trick. So, for example, I'll pick somebody today. Okay. Here we do. So have you ever seen this where you put the dollar bill between your fingers and you said, I'm going to drop it, and if you catch it, you get to keep the dollar? You ever done that?
I know the one where if you drop a credit card on the wall,
Yeah, I've seen that one. I've seen that one. Well, this is another one, before they did that, they did this one. And so here's what you don't do, okay, ready? Here you go.
Catch it, you might keep it.
1, 2, 3. That's what you don't do, okay? You don't do that. First of all, you don't let them know when you're gonna drop it. You see that? Number one, don't let them drop it. Number two, you don't let their hand be able to travel with the dollar bill. Open up. You don't let their hand be able to drop it. See? Number three, ready? You don't do the whole dollar bill. You do half of the dollar bill.
Oh, that's hard.
Okay, now, next, when you get ready to drop it, you don't let them know, you just drop it.
Dude, it's so slow.
Now, what I want you to do is, I don't want you trying to guess when I'm gonna drop it. I just want your eyes to say, when I see you drop it, I'm going after it.
Well, a reflex from that.
What?
It can be.
Now, I'm gonna tell you, I'm gonna show you the physics of this. You know why you wanna do it over and over and over? When I show you the physics, you only miss it by a few thousandths of a second. And so that's why people think, I'm gonna do it again, And you do have to be careful because now he's mad and he says, I'm getting that dollar and I'm gonna try to guess when he's gonna drop it. See, if he tries to guess,
Bro, you didn't even guess it right.
okay, I know, I see.
You try.
The idea, wait a minute, the idea is not to guess, okay? The idea is say, wait till you see the dollar bill drop and then see if you catch it. So, I'm gonna have you do a project later where you are gonna build a stick. And it's gonna be a stick called a reactometer, and you're gonna do an experiment. You get to design your own experiment and go find people, and some of you are gonna find little kids, and some of you are gonna find older people, and some of you are gonna find, anyway, you can design your own experiment based not on a dollar bill, but on a stick. And the stick is gonna be marked by you, and where they catch it, it actually is translated into how many seconds it took them, or how many hundredths of a second. That's called a reactometer. So let me show you real quickly the physics of this, and then the rest of the period we just want to study. And by the way, if you want to do this at break or during lunch, you should try it. But it's even better. The trick's even better if you know how it works. All right. Does everybody have a calculator? All right. I will show you why the dollar bill works. Why the dollar bill trick works. All right. Is everybody ready? Here we go. Now, even though there's air resistance, and I do take a chance of losing a dollar bill because if it's not really kind of flat, if it's kind of wrinkly a little bit, it'll be a little bit slower than I want it to be. But let's take a look here. A dollar bill is about 15.5 centimeters long. So I never do that. What's a half a dollar bill? It's about 7.75 centimeters long. Are you with me so far?
Yes.
So what we have to do is, I need half a dollar bill to fall through your hands before you can react with it. You get that? That's how I get to keep the dollar. So I'm going to take this free fall equation. See the distance equation? I'm actually going to use that. Now, I'm going to rearrange it, multiply both sides by 2. What happens if you multiply both sides of this by 2? You get 2d equals, are you with me in algebra? You guys know algebra, right? If I multiply both sides of this equation by 2, it'll get rid of this guy here, won't it?
Yes.
It'll be 2d equals gt squared. Now, I'm looking at you because I want you to understand this trick. And when you do your reactometer experiment, you got to do the same thing. Now, divide both sides by g, little g. Okay? Now take the square root of both sides. All right, here we go. How much time does it take for half of a dollar bill to go through your hands? I'm going to solve for time. You get it? So what is 2? 2 is 2. What is the distance? I can't put 7.75 centimeters because little g is in what kind of units? It's in meters, isn't it? So I change 7.75 centimeters into 0.0775 meters. Are you okay with that? And a little g officially is 9.8 meters per second squared. Now what's going to happen is you put in your calculator, it'll be this times that divided by that. But look at the units. Did it? Cancel. Cancel. Square root of second squared is seconds. And here's what happens. It should take about 0.1256 seconds to fasten your hands. Now the closest fraction I know of to that is 1/8 of a second. It takes about 1/8 of a second, and what they found out, a lot of researchers, some people's reaction times are faster than others, but one of the fastest reaction times of any human is 1/7 of a second. Now, you think I'm going to lose my dollar, but what is 1/7 of a second? 1/7 of a second is 0.143 seconds. 1/8 of a second, by the way, did you know that an eighth of a piece of pie, an eighth of a pie is less than a seventh? You don't like that, do you? Well, 8's bigger than 7. No, 1/8 is not bigger than 1/7, is it? 1/8 of a pie is smaller. So guess what? It takes an eighth of a second for a dollar bill goes through your hands. That's 0.125 seconds. How far? The fastest human reaction time is around 0.143 seconds. And so you're going to miss it by 18 hundredths of a second. And that's why people want to keep doing it over and over. They can't believe that they can't get it because they only miss it by 18 hundredths of a second. Get it? Anyway, I thought I'd like to show it to you because that's a little dollar bill trick. And when you eventually will make one of these. I'll show you what they look like. Now this person last year, they made theirs the minimum. I'll tell you all about the project after the test. I'll wait till after the test, and then next week I'll talk about the project. So this person did a stick, and they marked every centimeter. So every centimeter has to be marked, and then you plug those numbers into that equation, and you calculate. Hey, 5 centimeters is that much. That's many seconds. This many seconds. This many seconds. And so what we did is there's my zero. Here's my zero line. See that? And then what you do is you do an experiment with somebody, and some people like to talk, have music playing. Some people like to tell them, hey, tell me your multiplication tables. Blah, 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 blah. Okay, and then they catch it, and you find out what the reaction time was. You see that? And they do it more than one. Blah, 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 blah. Okay, and you do it 3 times, you find their reaction time. So what you'll be making is something like this, and there are different styles. Here's one style. Here's another style. There's big clubs. This is the big club style. You don't have to do that. Here's another style. Here's another style. They want to make it flat. Okay. Here's somebody who designed their experiment said, I wonder if the thickness of the pole you catch has anything to do with reaction time. And they made 2 of them. Wait, we won't even worry about the project till next week, okay? And so next week, and I usually give you like 2 weeks. I usually give you like 2 weeks to build the stick and do the experiment. And sometimes it takes that because, I've had people say, at lunch, they get people to volunteer and do the experiment. I'll tell you all about how to do the experiment later, okay? All right. And the last thing here is there was an article, and every year I ask a question on this, and they think some people think it's not fair. You asked a question about something you didn't do in class. Well, I thought this was an interesting article. Didn't you read this? See, some of you, I asked you to read this chapter more than once, and I know some of you haven't. And that's a problem because what was this article about? Did anybody read it? I thought it was pretty interesting. And a lot of you I know like sports. And it's about a thing called hang time. Hang time. You ever heard that about in basketball? Okay, and then there's some people you think, whoa, man, I can't believe it. When they jump, they're in the air for like 3 seconds or something like that. Oh, that's false. That is false. Okay? Anyway, if you read this article, you will find out that even though some people appear to be in the air longer than others, only because they're still pushing off when their toes still in contact, they're still not in the air yet. And then they come down that same way. so it looks like some people are in the air for that many seconds. But it says down here, no basketball player is known to have exceeded a jump of more than 1.25 meters, 4 feet. No player jumps more than 4 feet high. None. Setting this into equation in there, it says here that your half of your hang time would be 0.5 seconds. If you double it, the most anybody could possibly have, and they haven't yet, is only 1 second. So if you thought somebody had a hang time of 3 seconds, it's not happened. That did not happen. 2 seconds? That did not happen. Now, anyway, I thought that was interesting. If you want to read that, there's an article. So, for example, if you knew somebody was in the air for 1 second, how much of that 1 second was actually falling? How much of the 1 second was used in not going up, but coming down? How much? Oh, I lost you. If the total hang time was 1 second, how much that time was spent falling? Half. So couldn't we use the free fall equation? What was the distance that they fell from? Distance equals 1/2 t squared. And if you said it was half of a second, you put that in there and you find out, wow, the most you jumped was about a meter. The distance was only about a meter in the air. I shouldn't say only, because how many of you can jump? Some of you in here probably could jump a meter. It's possible. It's possible. Anyway, what I thought we'd do is review. Let's review it. I'm going to tell you what the test looks like. So, excuse me. So we know it's chapter 2, 3, and 4, but by far, the majority of the test is chapter 4. You get that? Okay, so now, what kind of things would be on chapter 2? Well, that has to do with vectors, didn't it? There were 2 things in chapter 2. One of them was vectors, and one was that thing called equilibrium. Do you remember that? So, if an object is either sitting still or moving in a straight line at a constant speed, it's at equilibrium, isn't that right? What does that mean? Tell me about the forces acting on an object. Wow. You give me some weird looks today. On chapter 2, there's only 2 ideas. One of them was equilibrium, and one was vectors, right? Tell me 3 things you know of so far that are vector quantities. Let's see if you can do that. What are 3 things you know that are vectors? You're scaring me. This is scaring me. Yes?
Acceleration.
What?
Acceleration.
Okay. You gave the hardest one. Acceleration is a vector because it has to do with change in velocity. Were you going to say velocity? And so velocity is a vector. And then what about the other one? Okay. So right now, there are 3 things that you have to say direction matters, doesn't it? So when we were at equilibrium, the net force, what was the net force on an object at equilibrium? 0. So you had static, you can have static equilibrium, or remember the dynamic, moving at a constant speed. In either case, your net force is 0. Now, then we learned about vectors. Remember how vectors have a tail and a head? Remember that? And then how do you add vectors in physics books most of the time? What's that method called? Okay, so if I want to add this vector and this vector, how do I do it? I put their two tails together. So here's the first vector, and here's the other vector. If I put their 2 tails together, right? What's step 2? You cannot be this foggy about this. Don't you have to redraw this one up here parallel to it? And don't you have to redraw that one? Okay, and this is where I started from, right? And what is the resultant vector? What is this plus that? It's the resultant, right? And how do you draw the resultant? It's the what? The diagonal, isn't it? Isn't that right? Now we had a whole worksheet on that, didn't we? Okay, so those are some of the questions you might find on the section that has to do with vectors and equilibrium. So that's pretty much, we spent a lot of time with that actually, didn't we? Right now I have no plans on using trigonometry on the test because I already gave you a grade on that. So I don't see myself using the trig thing. It would have to be like a bonus question or something like that. Okay, now, what about chapter 3? Chapter 3 had to do with inertia. And remember that thing called frames of reference? So remember, if a person's out there sitting on the equator and you're sitting right next to them and they don't get out of bed for a whole day, I say, were they moving? You said, no, I watched them, they didn't move at all. But what if I'm not on the earth? What if I'm looking at them from a frame reference not on the earth's surface? Then I saw both of you move past me at around 1,000 miles per hour, didn't I? So all motion has something to do with that. Here's another thing. If a jet is flying at 1,000 miles per hour, and I know the engines are pushing the jet this way, and it says 1,000 miles an hour, 1,000 miles an hour. It has a constant speed of 1,000 miles an hour. The engines are pushing the jet that way. How can I have a net force of 0 on it? How can I have a net force of 0 when I know the engines are pushing it with a lot of thrust? But I know the net force is 0 because he has a constant speed. Is that right? And we talked about this. We had to do with cars. What else is going on here? There has to be something pushing the jet that way. And what was that called? Air resistance. Is that right? Now, you don't like that because you see this jet, and you see the jet engines on, and you said, I know it's pushing, it's just like the car going down the road. I know the engine's pushing the car down the road. Why is it going at a constant speed? Why? It has to have a net force of what? 0. There has to be another force acting on it. And we spent time with that, and that was inertia. Okay. And then chapter 4, if you take chapter 4, that's where he had the packet. Let me see if I can find my packet here. And I would study, okay, for example, let's go back to the packet. There are 2 vocabulary words. One of them is called kinematics and one called mechanics. Which one is just the mathematics of motion? Not necessarily the cause, but just plug and chug and get the numbers. Which one's called just the mathematics of motion? Now, if you volunteer the answer, I can move faster. If you sit here and nobody says anything, I slows everything down. It's sitting right in front of you, and you've already answered 2 in a row, so I'm glad you do know, but everybody in here should be looking at their thing and saying, kinematics. Kinematics is just the mathematics of motion, right? Mechanics would be the study of motion and what causes that motion, like that. All right. So Galileo was the big, kind of the big hero of the kinematics world. He figured out a lot of things that had to do with the mathematics of motion. And then Newton came in later. We'll talk about Newton later. All right. What's the simplest kind of motion you might study? What's that? What's the fancy way of saying it? Linear, uniform motion, uniform linear motion. What does that mean? Straight line, constant speed. And what would that look like? And I knew you didn't like it. I took off what would it look like if I could look at an object every second, and if it's going at a constant speed? What would it look like? I see you, then I don't see you. Then I see you, I don't see you. What would it look like if you cover the same amount of distance in the same amount of time? What does that mean? Constant what? Constant speed, isn't it right? Now, do you know what is the acceleration of this object? Ooh. What's the acceleration on this object? 0. Acceleration will never tell you how fast you're going. Never. It'll tell you how fast your speed is changing. Got it? what's my acceleration? What's the final velocity minus the initial velocity over time? 0. Get it? I'm sorry. I made a mistake there. All right, so anyway, so we also looked at not only through the lens of the leaky oil or the strobe light, we also looked at this equation through the speed equation. Remember the speed equation? And you could rearrange the speed equation. And we should know that. And then another way we looked at it, what's another way that we looked at it? Was graphically. Let's look at that again. See, if you're not spending any time with this, except, if you come to class and just pay attention, you can actually do pretty well. But if you're forgetting things, then you probably need to spend some time with this. What is this a graph of? Distance, time. Distance, time, Distance keeps getting bigger, time gets bigger, distance gets bigger. They must be directly proportional because look at the graph. Is anything constant here?
Yes.
What is it?
Slope.
And the slope is d, whatever's on the y-axis over what? And what is d over t?
Speed.
Oh, that's speed.
Whoa.
So this is a graph of constant speed. What about this one? If the slope of a distance time graph is speed, then you have this speed, and you have this speed, and you have this speed. Well, you have many speeds, don't you? This is not uniform motion, isn't it? It's some kind of acceleration. Acceleration means you're going faster or you're slowing down, right? What about this one? Speed time graph. Let's see, is time 1 second, 2 seconds, 3 seconds, 30 miles an hour, 30 miles an hour, 30 miles an hour, 30 miles. What's that?
Distance.
What does this graph show?
Constant speed.
That's the
Constant speed. Ah. And here's a tricky question. I think you can do it. Some people actually have computer programs that can find the area. So let's say you're on a trip and 1 hour, 2 hours, 3 hours, 4 hours later, why would you want a computer to find the area underneath your graph at the end of 4 seconds or 4 hours? What would that be? What is the area of a rectangle? What is the area of a rectangle? Isn't it length times width? Isn't that right? Or height, whatever your teacher calls it. Isn't that right? In this case, what's the length? So the area is what? Speed times time. Speed times time? Why would somebody want to find the area underneath that graph? Well, what is speed times time? I lost you on that. What is speed times time? It's distance. If you find the area underneath that graph, it tells you the distance that you went. What if I found the area underneath this graph? And you have to use calculus to do that. You have to use calculus to find that area. What would that give me? Distance. So whether you're going at a constant speed or not, I could find your distance by finding the area underneath of that graph. What about this one? What does this show? 1 second, 2 seconds, 3 seconds, 4 seconds. Acceleration is 10 meters per second squared, 10 meters per second squared, 10 meters per second squared. Constant what? Constant acceleration. Does that mean constant velocity?
No.
It can't be. If you're constantly accelerating, you have to be changing speeds all the time, don't you? Acceleration will never tell you about how fast you're going. All right. Let's see. Okay, what else can I say? Well, let's go back. And what is the what's the difference between instantaneous speed and average speed? Yes.
Instantaneous speed is just the speed of one given period of time. And the average speed is, it's like you add up all of the distance over the time.
Okay, so in my car, the speedometer gives me what?
Your instantaneous speed.
Instantaneous speed, doesn't it? But if I take a trip and I slow down, speed up, slow down, speed up, I have many speeds, didn't I? So what's the best you can come up with if you have many speeds? And that's total distance divided by what? Total time. Isn't that right? Okay, now, what's the difference between speed and velocity? keep looking at you. You gotta give me some kind of, oh yeah, I got this. What's the difference between speed and velocity? Jessica, you know.
Speed is how fast, and then velocity is how fast and in what direction.
Right, so which one's a vector?
Velocity.
Velocity is a vector quantity, isn't it? Speed's a scalar. Okay, now if you and I are just talking about a car going down the road, I could interchange the words speed and velocity because it didn't even matter which direction the car was going. You get that? But it would matter. There are some times where it matters. Hey, can a car run into you going to 60 miles an hour and not hurt you? Yeah. What if you're going 59.5 miles an hour in that direction and they come up behind you and hit you at 60 miles an hour? See? So that direction makes a difference, doesn't it? What about this way? Not good. Not good. So there is a time, if I'm a pilot and I say, hey, the city I'm going to is due north. And somebody says, hey, what's the wind speed? Oh, the wind speed's, you're going to 800 miles an hour. The wind speed's pretty high, 50 miles an hour. 50? Oh, good. It'll push me to the city. And he takes off, and he never makes it to the city. He's way off. What happened? He didn't ask for a wind speed. What he should have asked for what? Wind velocity. Because if you're going this way and the wind's going this way, your plane's going to go that way, isn't it? You're going to miss the city unless you point your plane that way. See? And that's what they do. Of course, now we have GPS and computers, but every pilot has to know how to do it just in case something goes bad. They still have to know how to do it. Now, let's go, what is the next one? And here's the speed equation. What about non-uniform motion? What do you call it when you're not maintaining the same speed? You're going faster, you're going slower. It's called acceleration. And what is the definition? Change in velocity divided by time, or delta V over delta T. Now, how do you find the change in anything? How do you find the change in anything? And this is all in your notes. I'm just reviewing it. The second value minus the what? Okay, so what's VF minus VI? That's what you were trying to say a while ago, right? Okay, you were trying to say it a while ago, right? Delta V.
Oh, yeah.
Delta anything is the second value minus the first value, isn't it?
What was acceleration?
Yeah, that was, and over time. And so, anyway, we have to be a little careful here because velocity is a vector, so that means acceleration is a vector too, doesn't it? All right, ready. I've talked about this before. What if your speed is increasing, meaning delta V is a positive number? If speed's increasing, then what would you call what kind of number do you get for acceleration? You get a positive number, don't you? If you do the mathematics and the acceleration comes out to be a negative number, what's happening to that object? It's slowing down, isn't it? Okay? And then we had the whole thing about little g. Okay. Now, I think if you could go home and recreate this without looking at it, then you should be pretty good with little g. But when do you use this equation here? When do I use the v equals gt? When do I use that?
Speed,
That's how fast I'm going
instantaneous.
with constant acceleration. Doesn't the Earth, here, I always have this question on the test. What does the Earth give this pin? Constant acceleration? Constant velocity? Both or neither? What does the Earth's gravity do to the motion of that pin? Does it give it constant velocity? Constant acceleration? Both or neither? Yes? It does. What about velocity? No, it keeps getting faster and faster, doesn't it? Or it might get slower and slower if I throw it this way, doesn't it? It's not constant velocity. It's constant acceleration. And so if I want to know how fast are you going after so many seconds of free fall, I use this equation, right? That's free fall, how fast. What's this equation for? Free fall what? It's in the book. The book actually says free fall, how fast? And they spend a whole 2 pages talking about this equation. Then they say free fall, how far? And they spend 2 pages talking about this, don't they? Is that right? Okay, so what's one I don't have? What I wouldn't use that for what you said, average speed. For example, here, what if I was going in the first second? Here, that's a good question. Okay. Oh, I didn't even catch that mistake. This person made a mistake. They should have just put a 5 here because they had the units correct here. If you're going from 0 and you go up to 10 in 1 second, what was your average speed? Well, I was going 0, then I went 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What was my average speed? You add these up, divide by 2. What's the average speed? 5 meters per second. Oh, 5 meters per second. Now, if you average 5 meters per second, how far did you travel during that second? 5 meters. Now, notice I don't use that equation for these, did I? I use that equation for total distance. Here, plug in 1 second. What do you get? 1 squared times 5. That's 5. Let's do another one. Ready? What's the average speed during the second? 15. And how far would you go during the second? 15 meters. What's the total distance you go? 20. Or, plug in a 2 here. What's 2 squared? 4 times 5. It works out, doesn't it? All right. I'm almost done. 1 more minute, right? I have here, this is just for your, you don't have to use this. I put on here, somebody thought, well, what about other planets? You know, what's their little g? And Earth's little g is about 9.8 meters per second squared, or we'll call that 1 if you want. And what about Venus? Venus is almost the same size as the Earth, and it has this kind of gravitational constant. What if I went to Jupiter? Oh, man. Every second that you fell in Jupiter, you'd increase your speed by about 26 meters per second every second. See that? What about on the moon? Ooh, only 1.62. So as it falls, its speed only increases by about 1.6 meters per second every second. Wouldn't that fall kind of slower then? Yeah. Ah. Okay, I don't have you memorize that. Now, I put here, this is just some questions that the author wrote, and if you could sit with somebody and maybe go through those questions, if you could sit with somebody and go through those questions, that might jog your memory a little bit here. And I think that's about it. All right, well, thank you.